All right, let's get back to the last part of this lecture, and then we'll talk a little bit about the deadlines for the rest of the semester, and I'll go over homework for that are due next Tuesday, and I'll show you one of the resources on D2L that will be really helpful with homework 5. Cool? Sound good? Okay, here we go. Estimating the mean of a population. Woo! So this is the confidence interval method, which is a lot more realistic because you get a range of values that you think that your population's mean will fall between. And you're like 95% sure that the actual mean falls between those two values. So basically, what we've done so far is we know what the population mean is, and we're trying to find our sample. But most of the time, you're not going to know what that population mean is because you don't have access to them, because if you did, you wouldn't be using a sample. So you have to estimate the population mean using this confidence interval method from your sample to estimate what in the population that mean would be. Okay. So here's an example. So we have 36 people in this Society of Industrial and Organizational Psychologists, and their average salary is $56,000 and some change, and the standard deviation is 12,000-ish. Okay, so that's of our sample. So we want to see we want to kind of estimate what the population of everyone in this society, what their salary would be. So right now we have one single value, that sample mean of 56 for 53 and 58 cents of the mean, and we want to use that and the standard deviation we just saw to estimate that population. But if we look at the sampling error, there's a chance that we would get the exact same mean if we drew another sample. So this confidence interval indicates a range of values instead of estimating just one value that we think it would be. So if we drew 3 different samples of 36 people from that society, this is the range we think the mean would be between for each of those samples. Does that make sense? Because no sample is ever going to be the same. If I drew random numbers out of a hat and assigned each of you a number and drew random numbers out, from the first sample I drew maybe 4 people, and then I put all the numbers back in and I draw another sample of 4 of you, there probably won't be the exact same 4 people in both samples. So this is giving you an estimate of multiple samples so that you get an idea. Okay. So commonly you're going to use the 95% or 99% confidence intervals. In this class, we're only going to use 95% just to keep it easy, but in practice you may use the 99%. So the formula, if we have the sample mean and the number is less than 30, we would use this first formula. And if we are using the confidence interval formula for a sample that we have the standard deviation and any sample size, or if we have the sample mean and our sample is greater than 30, is this second formula, which I know is confusing, but it'll make sense. So how to interpret these? We are 95% confident that the true population mean of a sample with a sample mean of whatever falls between this lower limit, which is why there's a plus minus sign here, the lower limit and the upper limit. So here's estimating the mean of a systolic blood pressure. So we have the sample of 50. We have the sample mean systolic blood pressure of 120. And the standard deviation is 14.2. So what is our 95% confidence interval around the sample mean systolic blood pressure of 120? So first we're going to select this 95% confidence interval. Are we going to use the critical value z or t? So we look at our sample size, we have 50. So that means we should use the CVZ because we have a sample of greater than or equal to 30. So that's this formula here. So the confidence interval is equal to the sample mean plus or minus the critical value z times the standard deviation divided by the square root of the number in the sample. Okay. So again, the first step is state your desired level of confidence. For this class, we're always going to use 95%. Okay, cool. So here's the formula written out. So the 95% confidence interval is equal to 120. That was the mean we had, plus or minus this critical value z, times 14.2, which is the standard deviation, divided by the square root of 50, which is the number in our sample. So we don't use the z formula to calculate this CVZ value. If we're using a 95% confidence interval, the critical value z will always be 1.96. If you're ever going to use the 99% confidence interval, which we won't in this class, then your CVZ would be 2.58. Because they don't rely on sample size, they're just using that normal distribution graph. Those are the cutoff points. So just know, if you're using a CVZ in this class, it will always be 1.96. What does this mean? So this means that this is where our standard deviation falls. So we're looking to find 95% of the sample means fall in this middle portion here. So there's 5% that fall on either side of this graph. That's why you get the 1.96. It's also kind of showing if you had all of these individual samples, there's like one of them that doesn't contain that population mean here. Most of them will contain that mean. That's what the 95% confidence interval is saying. Some other factors that might affect this, I'll get back to the example soon, but I just wanted to touch on these couple things first. The sample size, if it's bigger, then your confidence interval is more narrow. A more narrow confidence interval means you are more precise with what your estimate is for the population mean. So I don't know how well you can see this from there, but here's a kind of like a chart across different income levels. If we have a sample of 10, it might fall between, the population might fall between $47-ish and $65,000. If we had a sample of 36, it would fall more between 52 and 62. So because it's a bigger sample, where the confidence interval gets smaller, and so on. If we had 100 people, it'd be even smaller because we're more certain of what that actual value is. So the higher level of confidence you want, the wider your confidence interval will be. So a 99% confidence interval is wider than a 95% confidence interval. A 90% confidence interval is narrower than a 95% confidence interval. This is one of the questions on the homework, a multiple choice question. So you can just come back to this slide when you get to that question. Be like, which one is it? Okay. And then here's some more examples, just showing you the effect of the level of confidence on the means. So if we're, in this first one, 99% confident, it would be between 50 and 62,000. If we're 90% confident, we're less confident, then it's between 53 and 59. Because we're less confident, the range is can be smaller. But there's a greater chance that the actual population mean doesn't actually fall in that window. Because now there's a 10% chance that the population mean is outside of this range. In this 99% example, there's only a 1% chance that the population mean is outside of this range here. So when you're choosing between different levels in the future, you have to decide, would you rather have a more precise mean or would you rather be more certain? It also depends on sample size. But again, for this class, 95%. Keep it constant, keep it easy. Okay, so now back to the example. We're going to calculate the confidence interval and limits. So here we have this fun formula. We know that because this is a sample size of greater than or equal to 30, we're using the CVZ of 1.96. So we fill in the formula, and then we do the plus one. I always do the lower limit first, so that's the minus. So 120 minus 1.96 times 14.2 divided by the square root of 50. Make sure you follow the proper rules of calculation. So you would do the square root first, then divide 14.2 by the square root of 50, then you would multiply that value by 1.96, and then you would subtract that value from 120. Make sure you do it in that order or you won't get the right answer. And then the same thing for the upper limit. Since this extra calculation would be the same for the first one and the second one, you just have to add the same number here to your original 120, and then you get 116.06 is your lower limit, and 123.94 is your upper limit. So what does that mean? Draw conclusions. We are 95% confident that the true population of a sample with a sample mean of 120 falls between 116.06 and 123.94. So our sample has the mean of 120, and from that information, we're 95% sure that the population mean falls between those two values we just calculated. Does this make more sense than the other ones? Probably. Okay. So here's another example. Given the sample of 16 with a sample mean IQ of 106 and a standard deviation of 12.4, what is the 95% confidence interval around the sample mean IQ of 106? So are we going to pick the critical value Z or T here? T. Because our sample is less than 30, we use T. So the formula is the same, except that the CVT will be different than the CVZ would be. So you fill in the formula the same way. 106 is the mean plus or minus the CVT times the standard deviation divided the square root of the sample size. How do we get this value? The t-table, the lovely t-table that we were looking at with the degrees of freedom. So first you calculate degrees of freedom, n minus 1. So our sample size is 16 minus 1 is 15. So then, now I have the table. Okay, so now you go to your table, that's on D2L, or you can print it out, whatever is easiest, and you find down here on the degrees of freedom column 15. Now, we're only using the 0.975 column in this class. So then we go to there and we find that the CVT for 15 degrees of freedom is 2.131. Then we take that number and we plug it into the formula here, and then we calculate the lower limit and the upper limit. And then we summarize it and we say that we're 95% confident that the true population mean of a sample with a sample mean IQ of 106 falls between 99.39 and 112.61. Does that make sense? Do you have questions about this? So there's one practical one of these questions on homework 6. Homework 5 is based on the other stuff we talked about before break, for the most part. Okay, so just a little recap of the main points of today's lecture. The sample mean distribution is the basis for the inferential statistics. So this is the basis of how we're going to be doing all the rest of things. That doesn't mean you're going to have to calculate these after you do homework 5 and 6, because you won't. But you need to know how to do them for homework 5 and 6. But after that, you can forget about it. It's fine. Z-values you use when you know the mean, the population mean and population standard deviation, or if you do not know the population mean and standard deviation and you have an n of greater than or equal to 30. T-values are used when you don't know the population mean or standard deviation and you have an n or sample size less than 30. And confidence intervals are used to estimate the population parameters from random samples from the population. Cool. Okay, so that's all the lecture, but now I'm going to go over a few things that will help you